A2 Further Maths, Yates Correction. Right, just a bit of practice from first year. What I'd like you to do, please, is have a go at this question. So you're running a 10% significance level test using a chi-squared approximation. So I'd like you to pause it, have a go at this question, and we'll compare results in a second. Okay. So the first thing you want to do is make sure that every single time you're running a hypothesis test, you are going to state the null and the alternative hypothesis. And it's always the same in chi-squared approximation tests, that you assume that your null approximation is there is no association between the two criteria. So in this case, there is no association between the weather and whether you win or lose or draw the game. The alternative hypothesis is the opposite to this, that there is an association between the weather and the result in the game. So those two are always the same for these chi-squared tests, so you just need to get used to writing those down straight away. Okay. So the second thing we need to do is complete the contingency table for the observed and the expected values. So the first thing I'm going to do is just complete the table. So we've got these results on the outside, these results added up downwards, a total of 90, which is what it said initially. And we can calculate the expected values now from this. So the expected values were always the same. Let's get my pointer on. They were always whatever the row total is, times by the column totals, divided by the grand total. That's what we're going to look at here. So expected value. So if I want to get this one just here, that is in the top row, first column. So it's the top row, it's the 37 times by the 40 divided by 90. And I can put that one in just there. This one, top row, second column, top row is 37 again, second column is 24 divided by 90. And so I could go and fill in the rest of that table of what I expect to get from these results at the bottom. That's what I would expect. You need to notice that none of the results are less than 5. Because they are less than 5, you would not be able to run your chi-square approximation. If they were less than 5, you would have to combine some of the things together. Okay, but every single one of our expected values is above 5, so there is no issues running our chi-squared approximation. Right. Once you've done that, we can calculate the values of the chi-squared approximation using this formula. The observed for each of the cells, take away the expected for their equivalent cells squared, divided by the expected. So I can fill the table in then. So it's the observed, which is 21. The expected, which is 16.44. So you're basically looking at the difference between those two results. We square it to make it positive, so we don't get just a zero amount at the very end, and we divide it by what we expected again. So we divide it by the 16.44, and that would get us that. So this one just here, observed 7, expected 9. So you look at the difference between those two by taking them away, you square it, and you divide by the 9.87 again. So we can fill in those results like that. So those are all our differences. And what this also does is it shows which of the possible results were the furthest away. So the bigger this number here, the further away from what you expected is important. So this one here, for example, cloudy draw, had the biggest amount of bias on it. We expected about 6, maybe 7 matches, but we ended up with 11. So there's quite a big difference there. Whereas this one was pretty much what we expected. We expected about 7, maybe 7.5, and we got 6, so it's not far off. Same with that one there. Okay. So if there is an association, you can also tell which ones had the biggest bias on that association. Okay, so what we're going to do now is just calculate the approximation by summing up all those possible results. So we can add them all up. There they all are. Work out that total. Gets you a grand total of about 8.92. You need to compare this to the chi-squared test, but before you can compare it, we need to know the degrees of freedom. Now the degrees of freedom were always rows take away 1, columns take away 1, multiplied by together. That does get us the knee value. So there we go, we've got 3 rows, 3 columns, so 3 minus 1 is 2, 3 minus 1 is 2, 2 times 2 is 4. We can get our table from our formula books, and we're looking for a 10% significance level, because that's what the question stated. And once we find that, there we go, we can get 10%, which of course is 90% on here, or 0.9. We can find the knee value of 4, and there we go, we have got a critical value of 7.79. So I'll just make a note of that critical value, 7.779. And now what we need to do is we need to compare. Was our value greater than our critical value? Did it go past our critical value? Now it did go past our critical value, so it passed that line. So therefore, the approximation or the approximate chi-squared statistic was greater than our critical value, so we can reject our null hypothesis. In this case, there was enough evidence to reject the null hypothesis, and that means that there was an association between the weather and the result in the game. So there is a result, there is a change in the weather, you would expect a change in the result of the game. Okay, so I'd like you to grab your notebooks out, because that was a revision from last year, but now we're going to look at just a slightly different, a slight amendment to when we have to run these chi-squared tests. So if the number of degrees of freedom is equal to 1, then the chi-squared approximation is overly biased. What that means is that you end up with a very biased situation if you have a very low degree of freedom. In fact, if it's just 1. Now, the only way you can get 1 is by a 2 by 2 contingency table. So for a 2 by 2 contingency table, if you're trying to work out the degrees of freedom, you do rows take away 1, columns take away 1, so you'd have 2 take away 1, 2 take away 1 gets you 1. In which case, the result you get will be biased. So what we do is we add in what's called a Yates correction. So the Yates correction is a very slight amendment on our table. And what it does is it still works out the observed minus the expected. It finds the positive value of those, that's when the modulus signs come in, take away just a half, and then square it. So it's this part that's different to what you previously did. Apart from that, everything else is exactly the same. You just have to do observed minus expected, make it positive. Okay, so we can ignore the negative. Then we take away 0.5 from that answer, then square it, and then divide by e. Okay. Notice that the modulus says it's changed the sign, and that's why it's a second year skill, because you've only just learnt what the modulus function actually does. Right, just be aware that if your table is reduced, so sometimes you reduce the table down, as I mentioned earlier, if the expected value is below 5, you would have to combine some of your results. If that happens and you reduce your table down to a 2 by 2, you still run the Yates correction. Okay, so as long as the knee value is only 1, you should run the Yates correction. Okay, so let's have a look at an example, similar to the last one. A computer game company investigates the age and gender of players of one of their games. Test using a 1% significance level whether the age of the player is independent to their gender. So I'll give you an opportunity to just write that down or very quickly put down in notes and that table of results. And what you'll do is answer it exactly the same as the previous one. So if you'd rather pause, have a go yourself, that's fine. Or if you want to just work through it with me, that's up to you as well. Just need to make sure you've got a decently set out in your notebook. Okay, so let's have a look. So state the null and alternative hypothesis in context. Exactly the same as before, exactly the same whenever you do one of these chi-squared tests. The null hypothesis is that there's no association between age and gender, and the alternative hypothesis is that there is an association between the age and the gender of the player. That's the first thing you state every single time, and it's always the same thing for a chi-squared. Okay, so we complete the contingency table the same as before, so you can fill all that out, no difference there, 53, 35, 8, and so on. Get to 8. Once you've got your observed table all filled out and you've got your extra rows and columns, that's because you need to fill out your expected values. So there we go, we can fill out our expected values. So 53 times 8 divided by 88, and so on. So we expect to get those values. What we ended up with these values. What happens next then? We notice that some of these values are below 5. Now the examiner will expect you to notice this yourself. So if you carried on going through the question and didn't notice that, you're going to lose marks. Right? You'll get hit a few times. So you need to make sure that you always check after you've done your expected table and said, oh look, here we go. There's a bit of a problem here. In fact, there's a problem here as well, that we cannot run the chi-squared test. We have to stop at this point. We can't carry on. What we're going to do is we're going to combine some of the rows. And so it's the obvious ones. Don't just combine two random ones. For example, don't do the under 10s and the over 30s together, because you've got the young people and you've got the older people. It would make more sense for you to combine these two categories together. So the under 30s then, and then the over 30s. So you've got a very clear, easy to separate group. Okay, so that's the first thing I'll do. Combine those two together. You can just do it straight away off the expected table. You don't need to do it back to this one, although that would work as well. So you can do it straight on this table, and we can combine those two together. So you'll notice you would get the same answers, that plus that, that plus that, and so on. Okay, so what you have to notice now, and again, the examiner will not tell you this, he expects you to notice it. You take that table just there, and you say, oh look, it's a 2 by 2 table. Now, because it's a 2 by 2 table, I will have to use Yates Correction. This is more likely to come up on your exam, because in the AS paper, this would not happen. Okay, so it's more likely to happen in the full A-level paper. So make sure you're looking for those two things. Is any expected values below 5? Yes, combine. Is it a 2 by 2 table? Yes, we have to use Yates Correction. Right, so when we're using Yates Correction, the only thing we do differently is we look at the observed. Be careful, the observed is those two put together, so it'd be 21. We got 27, so that's a difference of about 6. We modulus it, in other words, we make it positive. We take away 0.5 and then we square it. So we're using that formula just there. So there we go, difference about 1.16, because there's not much difference between those two. Then we got 25 and 32, so we compare those two, 1.21. Then we've got these two just here, so about 24, expect to get about 17, so 1.75, and then finally 1.85 because we got 11 and we expected to get about 17. So you can see there's quite a big variation between each of those numbers. It would have been even bigger if you hadn't used Yates Correction. Okay, so once we've got these bits filled in, now what we can do is we can finish off our chi-squared test. We've done now, we've finished with everything that's different. Now we carry on as we would have done previously. So we've got Yates Correction, we add up our values, put in there, and we get a value of 5.96. We still look at our degrees of freedom. We know what it is because we had to use Yates Correction, so we know it's 1. That's why we did it. And we also just make a note of the significance level. So it's 1%. So we're looking for 99 or 0.99 on our table. So there's 0.99. There's the knee value of 1. So that gives us a grand total, a critical value of 6.635. So 6.635. If we compare that to our value, 5.96 is lower than 6.635. It hasn't reached our critical value. It's below our critical value. So there's not enough evidence to reject the null hypothesis. So in this case, there is enough evidence to suggest that there is no association between the age of the players and their gender. Okay, so there's no significant evidence suggesting an association between them both, right? If you forgot to use the Yates Correction, then you would have got 7.07, which leads to a different conclusion because 7.07 would have been above it. So having Yates Correction in this case was a major difference. If you didn't use Yates Correction, you would have rejected the null hypothesis. So it's important to make sure the examiner will set it up in that sort of situation so that he can check very quickly whether you've got the Yates Correction on or not. Okay, so what I'd like to do now is just have a go in your statistics books, turn to page 46 and have a go at exercise 3B.